Sitting nearly 93 million miles from Earth, the Sun is the focal point of our solar system, with each planet and their moons orbiting around it. Even at this great distance, the Sun's spectacular energy can pose significant risks in our world. With so much hinging on what's happening on and around the Sun, it is critical for scientists to continuously monitor solar activity. From solar flares to solar storms that can interfere with Earth's electromagnetic field, providing accurate, timely warnings of potentially harmful space weather and its impacts on Earth is more important than ever before. That's where the Deep Space Climate Observatory satellite mission, better known as DSCOVR, comes in. When it launches in early 2015, the DSCOVR satellite will continue monitoring the constant stream of charged particles from the Sun, also called solar winds. These observations are the backbone of NOAA's space weather alerts and forecasts. Located approximately 1 million miles away, DSCOVR will orbit the Sun in a fixed position relative to Earth.
Occasionally, the Sun will have a large eruption of magnetic field, energetic particles, and if that comes towards the Earth and collides with the Earth's magnetic field, that's when you can get disturbances that we call solar or geomagnetic storms. Now, these geomagnetic storms can be very damaging to critical infrastructure on Earth, such as power grids, aviation communication systems, satellites in orbit.
Having a satellite in orbit that can provide us with advance warning if solar activity occurs that could create issues for our system is actually the first line of defense, if you will, for us to be able to take the appropriate action to protect our system from any impacts that could happen.
Experts estimate the most extreme solar storms could cause $1 to $2 trillion in damages and require a decade to recover.
Having some advance warning is critical to us for a solar storm or a hurricane. The advance warning we get from NOAA for hurricanes and other major storms, the National Weather Service, I kind of liken that to the same sort of thing we need, the same sort of warning we need from on a solar storm activity. So that's pretty critical because you can't reliably predict the storms from Earth-based devices. You need the satellite out there. So having that extra hour warning, I'll say ahead of time, allows us to begin to put procedures in place to protect our system. So whatever outages may occur, we can more quickly restore customers.
DSCOVR will join Composition Explorer, or ACE, and the Solar and Heliospheric Observatory, known as SOHO, and will also host NASA-funded secondary sensors for Earth and space observations. NOAA will manage DSCOVR and use its Space Weather Prediction Center to distribute critical space weather data to users within the United States and around the world.
DSCOVR data will drive our latest forecasting models that we're developing now. This will allow forecasters to provide forecasts. Currently, we just do nowcasts of the geomagnetic conditions, but forecasts of the geomagnetic conditions at Earth, not only for a global sense, but also regionally, so we can see what parts of the Earth will be particularly impacted by the geospace disturbances that come from the Sun.
NASA spacecraft takes GPS to new heights. Presented by Science at NASA. As any backcountry hiker knows, Global Positioning System, or GPS, trackers are crucial for navigation. But they can also be a little finicky. Units sometimes lose lock when you walk into the shadow of a canyon wall, when you point the units at the ground, or even when you make a sharp turn. Now imagine a GPS system flying through the vacuum of space at 22,000 miles per hour, rapidly spinning 43,000 miles above the surface of the blue planet below. Would it work? Turns out the answer's yes. NASA has developed a GPS navigation system for the newly launched MMS satellites that operates under these incredible conditions. On March 12th, the 4 spacecraft of the magnetosphere mission left Earth on a mission to investigate the physics of magnetic reconnection. Magnetic lines of force cross, cancel, reconnect, and bang! Magnetic energy is unleashed, with charged particles flying off near the speed of light. This process happens in many places. It sparks solar flares on the Sun, as well as powering magnetic storms near Earth. Understanding how magnetic reconnection works requires the 4 spacecraft to fly in a tight pyramid formation through Earth's magnetic field. Positioning is crucial. Speed and altitude are not the only challenges for the spacecraft's onboard GPS units. In addition, the MMS spacecraft spin Each one makes 3 revolutions per minute. Spinning adds a whole new dimension to trying to figure out where you are, said Ken McCoy, MMS GPS Navigator Product Development Lead at NASA's Goddard Space Flight Center. We have 8 GPS antennas on each spacecraft. As the spacecraft rotates, we have an algorithm running that allows us to hand off from one antenna to the next without losing the signal. During the first month, the team compared the MMS Navigator system with orthodox ground tracking systems and found Navigator to be even more accurate than expected. At the farthest point in its orbit, some 43,000, Navigator can determine the position of each spacecraft with an uncertainty of better than 50 feet. The MMS Navigator system exceeded all of the team's expectations. At the farthest point of the MMS orbit, of 43,500 miles, Navigator was able to receive signals from the GPS satellites and perform onboard navigation solutions. At the lowest point of the MMS orbit, Navigator traveled at velocities over 22,000 miles per hour. In comparison, GPS satellites orbit at 12,550 miles away from the Earth and travel at 8,600 miles per hour. And most satellites using GPS receivers are in low Earth orbits at altitudes between 110 and 1,250 miles. It's fair to say the MMS GPS is far out and moving fast. This system will be even more important during the second phase of the MMS mission, when the orbit will double in size and travel all the way out to 95,000 miles from Earth. Thanks to this extraordinary GPS tracking, the work of understanding magnetic reconnection can begin. Stay tuned for updates with precision from science.nasa.gov.